So is it audible?
Yes, sir.
Yes, sir.
Okay, so let us start then. So we will start today's lecture with these. These are called as Green's equivalences. Green's equivalences. These are actually equivalence relations, and they are defined on any semigroup, and they are very important as far as looking into the structure of a particular semigroup is concerned. We will see it later on how they help in identifying the structure of certain semigroups. So then, now let us start. Now, suppose you have a semigroup S. So if S is a semigroup, S is a semigroup, and A is some fixed element of S. A belonging to S be any element. Now, if you take this set, so if you take S A union the singleton A, so this is actually what? This is the set small s A such that small s is in S union A. So it is actually the smallest left ideal containing A. Is the smallest left ideal of S containing A. You can verify it. So you have to verify it that first it is an ideal, and then for any ideal containing A, it is contained in that ideal. So it is actually the smallest ideal containing A. And we denote it by this symbol S1A, and call it as the principal left ideal generated by A, and call it the principal left ideal generated by A. Generated by A. Now similarly, if you take AS1 means this set AS union singleton A. This is actually the principal right ideal generated by A. Is called, it is in fact the smallest right ideal containing A, so we call it principal right ideal generated by A. Principal right ideal of S generated by A. Generated by A. So likewise, you can define a principal two-sided ideal. Finally, you can define if you take this set AS union SA union A, and you just denote it by this symbol S1 AS1 is called principal two-sided ideal. It is actually the smallest two-sided ideal containing A. So we call it principal two-sided ideal generated by A. So these are the concepts of principal left, right, and two-sided ideals. Why I am defining these principal left, right, and two-sided ideals? Because these Green's equivalences, they are actually defined in terms of these principal left, right, and two-sided ideals. So let me define the Green's equivalences then. So an equivalence an equivalence an equivalence denoted by L on S is defined by the rule that is defined by the rule that two elements A and B of S, they are L related if and only if they generate the same principal left ideal. Okay, A, B belonging to S, A is L related to B if and only if the principal left ideal generated by A is same as the principal left ideal generated by B. S1A is same as, that is A and B generate the same principal left ideal. That is A and B generate the same principal left ideal. The same principal left ideal. So we say that ALB. ALB means I am actually saying that A comma B, they belong to this relation L. That is ALB if and only if the principal left ideal generated by A is same as the principal left ideal generated by B. And it is of course an equivalence. I will not verify that this L is an equivalence because it is trivial, just straightforward. So similarly, we define the equivalence R. Similarly, we define the equivalence R on S by the rule that A is R related to B if and only if the principal right ideal generated by A is same as the principal right ideal generated by B. So R is also an equivalence. So this is how we define two equivalences. One is L, other is R. So two elements are R related if and only if they generate the same principal left ideal. Two elements are R related if and only if they generate the principal, they generate the same principal, right ID. But you can have an you can have an alternate, or you can say equivalent description for these definitions, and this is in fact the proposition that is straightforward. It follows from these definitions. So what is the proposition? So it says that so this proposition says that so if A and B be elements of a semigroup S, if A and B be elements of a semigroup S, of a semigroup S, of a semigroup S, then A is L related to B if and only if and only if there exist some X and Y, there are some elements X and Y in S1 such that such that XA equal to B, YB equal to A, YB equal to A. Also, A is or related to B if and only if there exist some elements UV in S1 such that AU is B and BV is A. So this is actually an alternate way of looking at these two relations, L and R. Now proof is straightforward, it follows from the definition. Now suppose you have A and B, they are elements of a semigroup S. Then ALB, if and only if by definition S1A is same as S1B. Means what? If and only if SA union A is same as SB union B. Okay. So this means if they are same, then this is if and only if you can say that S1A is same as S1B. So this is if and only if B belongs to S1A and A belongs to S1B. Okay. Or you can say that if and only if now B is a member of S1A, so B has to be of the form XA for some X in S1. and A is a member of S1B means A has to be of the form some Y times B, where Y is in S1. So if and only if B equals XA, A equals YB, A equals YB for some X and Y, they are in S1. Okay, so we have done this ALB if and only if you find some X and Y in S1 such that XA is B, YB is A. Similarly, you can prove that A or B if and only if AU is equal to B and BB is equal to A. So the other case follows similarly. The other case follows on similar lines. The other case follows on similar lines. So this is the alternate definition of L and R. Now these are equivalences but not congruences in general, these L and R. However, we will just prove that this L is a right congruence and R is a left congruence. So note the equivalences L and R are not congruences in general. In general, however, we have the following. However, we do have the following. We do have this proposition. It says that L is a right congruence and R is a left congruence. L is a right congruence and R is a left congruence. And R is a left congruence. So first we will see that L is a right congruence, so the other follows on similar lines. So suppose A, L, B and S is some element of S. Then by this the above proposition, by above proposition ALB means there exists some X and Y in S1 such that AX is equal to B, sorry, such that XA is equal to B, XA is equal to B, and YB equal to A. Now, XAS equals BS. and ybs equals as. So again, by the definition of L, this implies that as lbs. So 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 if ALB, then we have shown that as lbs. So this means what? This L is right compatible. L is right compatible. Thank you. L is right compatible and hence a right congruence. And hence a right congruence. Now similarly, you can show that this R is left compatible and so R is a right congruence. So the other case follows on similar lines. The other case follows on similar lines. So this L is a left congruence and R is a, sorry, L is a right congruence and R is a left congruence. Now, we know that the intersection of two equivalents is again an equivalence. So if you have an equivalence L and an equivalence R, you take their intersection, that is again an equivalence. And we call that equivalence as H equivalence. Okay. Now, we know that now since the intersection since the intersection of two equivalences is again an equivalence is again an is again an equivalence. So thus L intersection R is an equivalence. Is an equivalence. So let us call L intersection R as H. We denote the equivalence L intersection R as H. Now the join of two equivalences is again an equivalence. Now since also the join of the join of two equivalences is again an equivalence. So let us denote this L join R by D. So these this H and D, they are also equivalences on S. Now we know that the giant of equivalences is not easy to describe, and we have seen earlier that if the relations these equivalences permute, then giant is their composition. So as seen earlier, if rho and sigma are equivalences which also permute, which also permute. Permute means permute means this row composition sigma is same as sigma composition rho. Then this join is easy to handle. In that case, rho join sigma, rho join sigma. Just 1 minute. Hello, 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 hello. Then rho join sigma is their composition. This is a well-known result, I think. Is rho composition sigma. Hello. Yeah. 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 I'm hearing you. Yeah. Yeah. I'm hearing you. Yeah. 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 I remember. Yes. O- Okay. Yeah. 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 Please. You please call me after 1 hour. I would be available. Yeah. I'm busy somewhere. So after 1 hour I would be free. Okay. Yeah. Yeah, I would be able to access. No problem. Okay. 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 Thank you. Thank you. Okay. Okay. So sorry for the interruption. So I had to take an important call. So ये एक वेल नोन रिजल्ट है, आपने पीछे पढ़ा है शायद, कि अगर आपके पास दो इक्विवेलेंसेस हैं और वो आपस में परम्यूट कर रहे हैं, मींस उनका कंपोजिशन रो कंपोजिशन सिग्मा सेम है सिग्मा कंपोजिशन रो के, तो उस केस में जो उनका जॉइन होता है, दैट जॉइन इज सिंपली देयर कंपोजिशन. And we know that the composition is easy to handle, because we know that अगर आपके पास कोई दो relations हैं, then their composition is easy to handle as compared to handling their join. So we are lucky enough that in our case, जो हमारा केस है, इस केस में L और R, L and all they are permuted, they permute, means L composition R is same as R composition L. तो उस केस में जो इनका जॉइन है D, D is nothing but their composition and we could easily handle this D. Okay, so this is what actually our next result is. Now we just write this proposition. The relations L and R permute. The relations L and R permute. That is, we have this one. This L composition R is same as R composition L. Okay. So let us see its proof. So suppose S is a semigroup and A and B are elements of S. Now let S be a semigroup. S be a semigroup. Let A comma B are elements of S, and suppose A comma B belongs to L composition R. A comma B belongs to L composition R. Now what we have to show, हमें दिखाना है ये दोनों बराबर हैं, तो हम एक्चुअली क्या दिखाएंगे, हम दिखाएंगे L composition R is a subset of R composition L. फिर उसी तरह से हम ये दिखाएंगे R composition L is a subset of L composition R. So I have chosen A and B in L composition R. I will show that it is in R composition L. So by definition of composition, there exists some C in S such that this A comma C belongs to L and this C comma B belongs to R. So this means A and C are, so this means A and C they are L related and C and B they are R related. So this means ALC and CRB. CRB. Now is it audible?
Yes, sir.
Okay, so ALC and CRB. Now अभी 4 मिनट के बाद ये मीटिंग खत्म हो जाएगी, so you आपको दोबारा ज्वाइन करना है. Okay.
Okay.
So ALC means what? There exists some X, Y, U, V in S1 such that हमारे पास क्या होगा, XA इक्वल टू C, XA C के बराबर होगा एंड YC इक्वल टू A, एंड देन दूसरी तरफ से आपके पास होगा CU इक्वल टू B एंड BV इक्वल टू C. ये इक्वेशंस आ जाएंगी, पहली दो इक्वेशंस आ जाएंगी बाय डेफिनेशन ऑफ L and the other two equations are by definition of R. Okay. Now, now if we write D equal to this element YCU of S, then if you calculate AU AU is, A की वैल्यू है YC, सो इट इज YCU, और YCU अभी हमने माना ये D के बराबर है, सो AU आ जाएगा D के बराबर। सिमिलरली DV क्या आ जाएगा, YCUV, ओके। और CU की वैल्यू क्या है, CU की वैल्यू B है, तो दिस इज YBV, ओके। अगेन BV की वैल्यू C है, सो इट इज YC, एंड YC की वैल्यू क्या है A। तो आपके पास आ गया AU इक्वल टू D एंड DV इक्वल टू A। Actually, this means that A is all related to D. A is all related to D. Okay. Now, now also, now if you take YB equals YCU, and YCU is D. And similarly, if you take XD would be XYCU, and this is going to be XAU, and this is equal to CU, and CU is B. So this means DLB. This means DLB. Now A or D, DLB. So this means A or composition LB. Or in other words, you can say that A comma B belongs to or composition L. So this means L composition or, sorry, L composition or is a subset of or composition L. Now similarly, you can show that or composition L is a subset of L composition R. So they permute. So thus R composition L is same as L composition R. So once they permute, I have mentioned the result. By that result, D, which is L join R, is same as L composition R, and it is also same as R composition L. So the join of these equivalences L and R, which is D, is actually now the composition of L and R, and L composition R is same as R composition L. Okay. Now we have defined these relations L and R in terms of principal left as well as right, but one-sided ideals. हमने इनको डिफाइन किया in terms of principal one-sided ideals. We have defined L and R in terms of principal one-sided left, respectively principal one-sided right ideals. And if we define a relation in terms of principal two-sided ideals, that equivalence we call as the equivalence J. Now so far अभी तक हमने चार equivalences define किए हैं, L, R,